So another question that seemed to confuse a lot of students had to do with optical activity and how it relates to stereochemistry. So we'll go over that real quick. Let's see here. Alright, so when we talk about optically active and inactive, what does that mean? Well, it has to do, if we had a flask, so let's pretend that this is a flask on a table, we're going to have some chemicals in it, right? So what they do is they shine some light. We'll say, you know, here's our flashlight shining some polarized light, and it goes through this chemical containing glass, right? And something light is going to be coming out the other end because it's shining through it. So what comes out through this end is what's of interest to us when we talk about optical activity. When something is optically active, these lights that are coming out, these little light rays, photons, whatnot, is going to be either rotated to some degree, or it's not. When it's rotated, that's what we call optically active, and when it's not, when it comes out exactly pretty much the same way when it was rotated, in other words 0 degrees, that's called optically inactive. So what can we talk about? Say this was active, what possible values could we have for it? Well, the idea is that we can have either plus values, for example plus 5 degrees, or we can have the opposite inverse of negative, so negative 5 degrees. Now 5 was an arbitrary designation on my part. This could have been, 30 degrees, it could have been 35 degrees, it could have been 99.9 degrees. So that was just arbitrary, but the key point is to remember that positive and negative, they're going to rotate in different ways. One's going to be rotating clockwise, the other one's going to be rotating counterclockwise. So it makes sense. It's pretty logical up to this point here. So it gets a little bit trickier when we talk about mixtures. So you've probably seen it, the term racemic mixture. So what is this? Well, it's pretty important to grasp. It's a type of mixture that namely consists of enantiomers. Now that is kind of what makes it up, but the most important detail about this mixture is that it's just not any mixture of enantiomers, but it's an exactly 50-50 mix of them. So with that in mind, if this, for example, wasn't 50-50, what if it was 49-51? It's no longer a racemic mixture. It has to be exactly 50-50 on the dot. And I'll tell you why. Because enantiomers, alright, so we have two different types. We have, say, one's an R and one's an S, right? These are what would you say, stereochemistry designations here. So R, we're going to say rotates light positive. Now this is another important factor. The way of the way of the rotation, in this case positive, has no direct correlation with R. For example, we could have just easily have said that the S rotates it positive. The way that it's positive or negative is determined by experimental tests done in the lab. It's not something that is so simple as to say R equals plus or S equals plus. No, you have to go into the lab and calculate it, but you don't have to worry about that because I don't think you have to do too many experiments on your exam. So continuing on with this example, we're going to say that R is plus in this case. That means by default our S is going to be the minus. So if we want a racemic mixture, that means we want 50% R, 50% S. In this case, and in all cases, whatever we say that our R enantiomer rotates it, we're going to pick an arbitrary number. For simplicity, we're going to say 5 degrees. So our R enantiomer rotates light itself 5 degrees. So in other words, if we had a flask of just this enantiomer, no mix, there's no S in there, just R, 100% R, our result from light passing through that flask is going to be a positive 5 degrees rotation. So carrying on now, if we had, for example, 100% flask of just the S enantiomer, it's going to be, you guessed it, negative 5 degrees rotation. So it kind of makes sense now when we say a 50-50 mix. What happens if we do the math? We don't even need to do any kind of calculation because it's rather obvious in this case. If half is plus 5 and half is minus 5, well, those are exactly going to cancel out, and we're going to get a 0 rotation, which means, in other words, inactive. Let's go a little bit further and say that the R enantiomer rotates at 10 degrees, and the S enantiomer rotates at negative 10 degrees, alright? But now, let's say that their ratio is 48 to 52. Alright, so yeah, you always want to check your math and make sure that your ratios there add up to 100%. Don't make silly math mistakes like I almost did. Cost yourself points on the exam. So 48 to 52%. We can tell a couple things here. One, right off the bat, by looking at our percentages, it's not 50-50. So is this going to be a racemic mixture of these two enantiomers in a flask? No, it's not going to be, because we need that 50-50 once again. So we aren't going to have a racemic mixture. From that, we can tell that it's probably going to be a optically active solution. So let's go on a little bit and carry it on and find out something else. Our question may be, which way is the light going to be rotated? Is it going to be rotated positive? Is it going to be rotated negative? Well, there's another way to figure that out, which, you could do math, or you could just look at it and use your reasoning for simple circumstances like this. If we have 52% of a negative number and add that to 48% of a positive number, what number sign are we going to get? Well, we know if it was 50-50, if the scales were balanced, it'd be 0. In this case, the scales aren't balanced. It's tipping a little bit toward our negative side, right? So 52% is beyond 50% of our negative. So the scale is going to be weighing down toward our negative designation. So without even doing any more calculation, we can just say that it's going to have a negative rotation, right? So that's pretty much the gist of enantiomers and optical activity. Again, it's important to realize, like I said before, there's no direct correlation between R and being positive, S and being negative. That's just, we could have easily have switched these around and made our S's positive or an R's negative, but whichever way for it to be correct has to be determined in the lab. So this information will be given to you on the exam. What we did down here is more important on understanding how these numbers are used to determine optical activity. Thinking offhand, if there's anything else that's very important. I know there's a question on your practice exam about this very topic. Let me see if I can find it very quickly here. Alright, so another important thing, and this is just to memorize it, meso compounds are not optically active as a function of how they are with having a what would you say, a chiral type existence. They don't rotate any light. So meso, however you like to pronounce it, is going to be a molecule that always is inactive. So make a quick note here. Meso equals inactive. So that should be a data giveaway on your exam if you have a question like that. Another example of something that is inactive, well, I think we covered it. Racemic mixtures, 50-50% mixes of enantiomers, meso compounds. Something that's achiral isn't going to have any rotation of light. So basically the inverse of those or what you're going to say is active, namely a molecule that is chiral or non-racemic mixtures. You can see an example of a question that asks something like this. Number 14 on your practice exam. Spend the time to just look through each answer and understand why each answer is right or wrong, and how you could use each answer to make a question on your own, and how that could possibly be a question on your exam.